All right, we are on to part three in our series on waves, and this particular wave is a very interesting wave. So interesting that it gets its own chapter. So, chapter 11 is just all about tides. Um, so, let's talk about tides. A tide is experienced if you're at the shoreline as a periodic change in the height of the ocean surface. It feels like sea level is rising and falling once or twice a day, depending on your location. We'll talk about why that is um, during this presentation. But it turns out that the tide is actually a wave or a pair of waves that move around the planet every day. It's important to note that this is our one wave that is a forced wave. If the disturbing forces that we discussed in this session are gone, the tide is gone. It wouldn't keep going around the planet and around the planet like if you dropped a rock in a pond. The other thing to note about tides is that they have a very long wavelength. The wavelength roughly is half the circumference of the planet. Um, at whatever latitude you're located. So they are always very shallow water waves. If you think about at the equator, the circumference of the planet is 25,000 miles. So um, half of that is 12,500 miles, and then half of that is still 6,000 miles. So these waves have a huge wavelength, and so they're just basically moving around the water in the ocean basin. All of the water moves as the tide goes by. Now, what creates these? Well, our primary disturbing force is the moon. This is what sets all this in motion. The sun, we'll find, creates a tide as well. We'll talk about that at the very end. But we're going to focus on the effect of the moon. And so, specifically, what they mention in your book is we've got the gravity from the moon, which results in a set of motions with the earth, and that also triggers this third thing, which is the inertia of the water. So we will explain all these as we go through the slides. Let's take a look at this set of diagrams, and this kind of brings together where we get our two crests. So think of the tide as a giant wave with two crests, that's high tide, and two troughs, that would be low tide. The first crest is pulled toward the moon by the moon's gravity. Because the ocean is liquid, gravity can tug on that liquid and pull it up toward the moon. There is an earth tide, it's much smaller, so the ground does actually get tugged toward the moon as well, but not nearly as much as the water. So the moon's gravity creates a crest. Now you'll notice that that crest, which is on the left-hand side here, is one crest, it's pulled toward the moon. Where does the second crest come from? The second crest is what you see in the middle. The Earth and the moon actually doesn't go around the Earth. The Earth and the moon rotate around their joint center of mass. Now, the moon is much smaller than the Earth, and it turns out that center of mass is located within the Earth. But remember that the Earth is actually spinning around that little black dot that you see right there. And because of that, the water on the far side of the Earth from the moon gets thrown away from the center of mass due to this spinning action. And so that's what creates our second crest. And there are some additional diagrams in your book to try to explain this. Think of an adult and a child spinning around each other. The adult kind of circles around their center of mass, and the child kind of gets flung out like the moon does. When we put those two together, the two forces create two crests. A gravity crest pointed toward the moon, and what's referred to as the inertial crest, which is pointed away from the moon. So there's our two crests. And that basically is key to the whole thing. If you like science diagrams with force arrows, the force arrows are shown here in blue, red, and red. The force arrows combined, actually that's the red arrow. So the way force arrows work is the brown arrow is gravitational attraction, the blue arrow is inertia, and when you add the force arrows together you get the red force arrow. And you can see that's our kind of more detailed explanation of our two bulges. But again, gravity bulge on the moon side, inertia bulge on the side opposite of the moon, two crests, two high tides, and then the troughs in between are low tide. Now it'd be nice if that's all that happened, and you can see the resulting tides are shown on this diagram. We're looking down from the North Pole. You can see that this little island that they have drawn goes underwater at high tide twice a day, and then it's exposed at low tide also twice a day. So we have our two crests, one pointed toward the moon by gravity, one on the opposite side from inertia, and then the two troughs. And there's a diagram showing what that would look like. But as this slide notes, there are some complications. So let's take a look at those. Complication number one is the moon is not directly over the equator. So instead of looking at the view from the North Pole down, we are now looking at the view from the side. And we can see that if you are here in the northern hemisphere, you're going to hit that crest right in the middle at one point of the day. But when you get to the other crest, you'll notice you're on the side of it. And so you get a slightly lower high tide. This produces what we will call a mixed tide. You still have two crests, but one is higher than the other. And again, this is because the moon is not directly over the equator. Our crests are offset. One is offset to the north and the other to the south. And the position of the moon with respect to the equator changes over the course of the year. So sometimes it's north of the equator and sometimes it's south. Only when it's directly on the equator would you get two equal tides. So that's complication number one. Complication number 2 and 3 actually go together. The planet is not completely water. There are land masses. And so the continents block that tide wave. If we go back to this picture here, that wave would want to go just around and around and around the planet. It can't do that because it hits land. In addition, you recall the Coriolis effect that we've discussed with respect to currents and with respect to how the wind blows. The Coriolis effect also turns the tide wave. So when we put the continents together with the Coriolis effect, the tide crest actually rotates around the ocean basins in a very complicated manner. And so what this diagram that looks like it's full of spiders is trying to show you is how the tide crest progresses as it moves around an ocean basin. Where you see all the lines coming together in a point, there is essentially no tide. The tides are rotating around that point. In the northern hemisphere, they rotate around clockwise, like this. You can see my cursor. In the southern hemisphere, they rotate counterclockwise. So those are our other complications. Let me go back to that. So our three complications, remember, are moon's not directly over the equator. That gives us these mixed tides. And the tide wave actually rotates around the ocean basins. And when we put all that together, we end up with three different types of tides. Some places actually get those two equal high tides a day. That's on the right-hand side. Those are coastlines colored in green. Some coastlines only get one high tide a day. That's the coastlines colored in yellow. And some coastlines get the mixed tide, and you can see that on the left, and those are covered in red. Which tide you get results from a complicated interaction of the tide you expect plus those three complications. But that's not all. There is one more complication, and that is one that we set off to the end here, and that is the sun. The sun creates its own tides, just like the moon does. The big difference is that the sun's tides have smaller crests. And what happens is that the sun tides interfere with the lunar tides. So we get a wave interference pattern created by the interaction of these two sets of waves. Now, this interaction occurs over the course of roughly 28 days or a month. So, sometimes during the month, and let's go to this picture right here, the Earth and the moon and the sun are lined up. This gives us what we call a spring tide. The crests of the sun and moon tides, the sun tide is dark, the moon tide is light. The crests of the tides align, and we get an extra high high tide and an extra low low tide. Sometimes, when you look up in the sky and you only see half the moon lit, this is the position of the moon with respect to the Earth and the sun. In this case, the tides have destructive interference. The crest of the solar tide sits in the trough of the lunar tide, and the crest of the lunar tide sits in the trough of the solar tide. This gives us a smaller tidal range. So that's our interference pattern. The way this actually looks is like this. You can see the crests and the troughs over the course of a month. The spring tide refers to the constructive interference. This is not a seasonal term. So spring tides happen twice every month, not just during the spring. So twice every month. And the neap tides also occur twice every month, although only one is labeled here. The second one is at the beginning of the diagram. The spring tide represents constructive interference, where the waves add to each other, and the neap tides represent destructive interference, where the waves subtract from each other. So that is our final complication, and it gives us the monthly neap spring tidal cycle. And that is the last for this slide presentation.